Hello again. This is the first of a series of lectures on serial rings where we aim to prove a couple of prominent decomposition theorems on serial rings. And this is a graduate level lecture, of course, and there are some references that I would like to highlight. These are three of the great books that I would happily recommend to anyone who is interested in the theory. But we will follow the first one more closely than we will the others, although the others are very nice books too. The first one is a book by Alberto Facchini, Professor Alberto Facchini of Padua University, who basically wrote the book to present the solutions to two long-standing problems, one asked by Warfield and one posed by Krull. And since it's very aim-oriented, it's one of my very, very favorite books. And although we will be following the book in terms of its layout of results and many a time its proofs, we will present a different proof from time to time, or a different layout of the same proof in the book. So be ready for such differences, or in terms of proofs offered to the results. And let's talk about a couple of preliminary notions that we'll be using throughout the presentation. Let me remind you of the local ring first. A local ring is basically one that satisfies the following equivalent, any of the following equivalent conditions. So the first condition says that the Jacobson radical is a maximal right ideal. If that's the case, then it is the unique maximal right ideal. And since R is a cyclic module over itself, it is the largest proper submodule, or largest proper right ideal. And same thing goes for the left-handed case. The second one is useful in our applications. It says the set of non-invertible elements of the ring is additively closed, and both conditions are equivalent to R over the Jacobson radical being a division ring. So the condition number 3 highlights the fact that a local ring is necessarily a non-zero ring. Let's keep that in mind, because the next one is a generalization of a local ring, which is allowed to be as the zero ring. So it is such a ring that R over the Jacobson radical is semisimple Artinian. For example, any Artinian ring is just like this. Any Artinian ring is semilocal. Any perfect ring is semilocal, or semi-primary ring is semilocal. Let's look at these. Let's recall a couple of basic results on idempotence. If E and F are two idempotents of the ring, then the group of R linear maps between E, R, and FR is isomorphic to the FRE as a group. And if E and F coincide, then this is further a ring isomorphism. So we can easily identify ERE with the endomorphism ring of ER. Okay, which is what we'll do. Now, this is the more general form of locality of a ring, which is defined for modules. So a module M is said to be a local module if it contains the largest proper submodule. Now, that's not the same as M having a unique maximal submodule, as is highlighted by this example here. You see here, the Q is the unique maximal submodule, but it is not the largest proper, because otherwise it would have to contain Z by PZ2. But in the case of finitely generated modules, the two notions coincide, because in a finitely generated module, every proper submodule is contained in a maximal submodule. So the unique, for a finitely generated module, having a unique maximal submodule and having a largest proper submodule are the same thing. So with that definition, we can restate the locality of a ring in these terms. R is local as a ring if and only if it's local as a module over itself on the right or the left. In the first lemma, we prove that the endomorphism ring of the ER, the projective direct summand of R, it's a local ring if and only if ER is a local module. And that if and only if RE is a local module as a left module over R. So all these three conditions are equivalent. Let's do the proof. Let's first assume that ER is a local module. And let's use the second condition that characterizes the local ring a couple of slides ago. So take two endomorphisms of ER and assume that F plus G is invertible. So we aim to prove that at least one of the F and G must be invertible. Notice this though, since F plus G is invertible, then the image of F plus image of G, which clearly contains the image of F plus G, has to equal ER. So now assume that F is not invertible and aim to prove that G is invertible. If F is not invertible, then F is not onto in this particular case. This is because if it were onto, we would have the kernel F contained in the radical, because kernel F would then be proper submodule, because ER being a local module is non-zero. So kernel F is contained in the radical, which happens to coincide with EJ, by the way, where J is the Jacobson radical. And the kernel of F is at the same time a direct summand of the right module ER, because ER is projective. And projective modules, remember, have this property that every epimorphism onto them splits in terms of the kernel being a direct summand. Okay? So now the two conditions on the kernel imply that the kernel of F is 0, which forces F to be invertible, contrary to what was assumed. So this is why F cannot be onto. But if F is not onto, and since ER is local, then image of F has to be contained in the largest proper submodule of ER as a local module. But then, remember, ER is the sum of the image of F and the image of G. This was shown on the previous screen. So that forces, and since the radical of ER is a small submodule, namely it's, remember what a small submodule is from one of our slides, or one of our videos that I posted here a while ago. I guess it was in the video about the Wedderburn Artin theorem. But anyway, so basically a submodule being small means that it doesn't add up to the whole module with any of the proper submodules of the module. So that's what RAD ER is like. So this means in particular here in this case that the image of F being small and adding up to ER with image of G forces the image of G to be the whole module. That's this equality. Okay. And let me go back, let me clear the screen a little bit. So this means G is onto, and then just like we proved the ontoness of F implied F being a monomorphism, the same holds for G, and so G being onto now, G has to be invertible, as is required. So the endomorphism ring of ER, which is isomorphic to ERE, is a local ring. Let's look at the converse and assume that the endo ring of ER is local. Then ER is cyclic, so it means it has at least one maximal submodule, and we just need to prove that it's the only one. So what we do to prove that, we take two. We prove a slightly more general, slightly stronger result, saying taking A and B to be arbitrary submodules of ER, adding up to ER, like this. And if you take them to be your maximal submodules in particular, it would give you the desired conclusion. Now, we will consider the following diagram. Remember, ER is now the sum of A and B. And A plus B over B is isomorphic to A over A intersection B via the mapping that takes each coset in the form B plus A, where A comes from the capital A, to A intersect B plus A. So A bar goes to A bar. So then we have two epimorphisms here. One, the projection of ER with respect to this decomposition, with respect to this sum, onto this guy here via this association, via this map, the vertical one. Okay, so each element of ER is expressible in the form A plus B, where A and B come from the capital A and capital B respectively, and that if you map it to, so the map that takes this guy to A bar is an epimorphism with kernel equal to capital B, whereas the horizontal arrow shows a similar mapping. This time it takes A. Well, it's actually the restriction of pi prime to A. It takes A to A bar. Now, remember that ER is projective and pi is onto. So there's a map F that completes the diagram commutatively, meaning that this equality will be satisfied. And also note that the kernel of pi is A intersect B and kernel of pi prime is B, as I said before. So now, if you work on this, if you work on this equality a little bit, you will see easily that f of b is contained in the A intersect B. And okay, now assume that A is not equal to ER. If A is not equal to ER, then we aim to prove that B is equal to ER. So assume this. Then this means that the image of F is not all of ER. So F is not onto, therefore F is not invertible. By the locality of the ring of endomorphisms of ER, then 1 minus F has to be invertible. Okay? So okay, let's apply this 1 minus F to the decomposition of ER into A and B. Then ER is equal to 1 minus F of ER, that guy being invertible, this guy being invertible. And it splits over the sum like so. So now remember this. Let's first look at the 1 minus f of b. It's obviously contained in b plus f of b. That's not hard to see that, right? And we already said in the previous slide that f of b is contained in a intersect b. Then f of b plus f of b is contained in b plus a intersection b, which is equal to b. So if we show the same thing for the image of a under 1 minus f, namely if we show that it is contained in b, then this will prove that ER is equal to b because of this equality here. It's a little bit more indirect than the proof for b, but it's easy. See, the pi prime, remember the equality of the maps pi prime and pi f because of the commutativity of that map, of that diagram, and then take any element a from the capital A, then pi prime of a is equal to pi of f of a. The respective images are shown on the bottom, right? So for example, the pi prime of a is just the coset of a intersect b represented by a. And pi does the same thing. Pi projects every element to the respective coset, so it takes f of a to the coset of f of a. So this shows what? This shows a minus f of a, which is 1 minus f of a, is equal to, is an element of a intersection b as desired. So now we know that both images, 1 minus f of a and 1 minus f of b, are contained in b, but then that's equal to a. That's equal to the whole module ER. Therefore, ER is equal to b as desired. So this concludes our proof. In the next proposition, well, what we say is factors of semi-local rings are semi-local. Actually, this is true for factors, non-zero factors of local rings. So maybe I should highlight that for local case. Non-zero factors for local case. Simply because the zero ring is not considered a local ring, but for semi-locality we don't have that restriction. So to prove this, just take an ideal and just write J for the Jacobson radical. Now, if you look at the Jacobson radical of the quotient ring of R by I, it's just the intersection of quotients of maximal right ideals of R containing I with respect to I. So it is the intersection of quotients like this, where B ranges over some of the maximal right ideals of R. And since that's equal to this guy here, we see that J is contained in that intersection. So passing to the factor ring, we get J plus I over I is contained in the Jacobson radical of the quotient ring. So then, because of this containment, this inclusion, this big quotient ring that you see here is an epimorphic image of this guy here, which in turn is isomorphic to R over J plus I. But you know, this denominator J plus I contains J, therefore this is in turn an epimorphic image of R over J, which is a semisimple ring. As you know, semisimple rings, epimorphic images are also semisimple. Therefore, so is our ring R over I, or divided by R over I over its Jacobson radical. That's what I meant. So this shows that R over I is a semi-local ring as desired. Well, I'm going to skip through the proof of the next proposition, but it's an important one. I'd like to leave it as an exercise for the interested viewer. It basically says that if R is a semi-local ring and M is a finitely generated module over this ring, then M is a direct sum of finitely many indecomposable modules. So M has an indecomposable decomposition. This is bullet number 2, but the bullet number 1 says something more general that is true for any module, let alone for finitely generated ones. So in that sense, it tells us that any module over a Jacobson over a semi-local ring mimics projected modules over arbitrary rings in terms of their radicals being equal to their product by the Jacobson radical. So, but again, I'm going to skip through the proof, but I'll let you see the slides and briefly stay on them, just so you can pause them if you choose to do so, and to look through the proofs. So here's how the proof goes. As I said, just stop this slide, pause the slide to look at the proof, to study the proof at length. Okay, now we'll stop skipping in the next slide here, right here, to go into the definition of the main object of our discussion here. We call a module uniserial if its submodules form a chain with respect to inclusion. So from the get-go, let me point out that uniserial modules don't have to be non-zero, unlike their local counterparts, and we call a direct sum of uniserial modules a serial module. So right uniserial and right serial rings, or left-hand sided versions, are defined in a similar manner. For example, a right serial ring means one that is serial as a right module over itself. Right uniserial rings are also called right chain rings. So uniserial right or left uniserial ring is alternately called a right chain ring, or a left chain, respectively, in reference to its right or left ideals being a chain, forming a chain with respect to inclusion. Here are some examples. The localization. I'm going to leave the details of their verification to the viewer. Localization of Z at any prime P is a uniserial ring, and non-trivial factors of Z, factors of Z with respect to non-zero ideals are serial rings. Semi-simple Artinian rings are serial rings. So are upper triangular matrix rings over fields. And Artinian principal ideal rings are special kind of serial rings, which we hope to go into at some point in our discussion. And for the specialist, let me point this out. There's something called a hereditary Noetherian prime ring, which is again generalization of Z, and factors of such rings with respect to non-zero ideals are also serial, just like z by nz is serial. So this is the more general form describing that situation. So is the ring of formal power series over a field K. This is a serial ring. So these are all serial rings. Now, so far we haven't distinguished between right and left seriality, which the next example with gamma does. Here, this is a right but not left serial ring, the gamma. Okay. This guy, the Q rationals considered as a module over the localization at a prime P, is a uniserial module which is not cyclic. So this example distinguishes uniserial modules from local modules. So not every uniserial module is local. But if it is cyclic, it is local, of course. It is cyclic and non-zero, then it is local. A similar situation with the Prüfer group here. This is a uniserial ring that is not cyclic and has nice homological properties too, like it's an injective module, all of whose non-trivial factors are isomorphic to it. Okay. Now remember the situation with the local idempotency generating local right or left ideals. The theorem there, it was a couple of slides ago, it said that ER is local if and only if RE is local, if and only if ERE is a local ring. So all these were if and only ifs. All these were connected by with biconditionals. The situation with uniserial replacing local is a little different. I don't know why we say non-zero here. So I'm going to erase that. Okay. I don't know how it got there. So just take an idempotent E. So if ER is uniserial, then ERE is a right uniserial ring. Let's prove that and then see that the converse doesn't hold. Just take two elements, x and y, from the ring ERE. We want to show that x times ERE and y times ERE, one of them contains the other. That's what we want to show. What we know, because of the locality, because of the uniseriality of ER, is that the right ideals generated by XR and YR, which fall in ER, of course, because X, you see, they belong to ER in particular. They all belong to ER. They all are contained in ER. So XR and YR are submodules of ER. And ER being uniserial, one of them contains the other. So let the larger one be XR. Since, okay, so you see, if you multiply the two sides of this inclusion by the idempotent E, the inclusion is preserved. Okay. Well, also remember this though, x comes from ERE, therefore x times E is equal to x, and similar thing goes for y. So if you replace here in this inclusion y by ye and x by xe, it reads this. And that's what we wanted to prove. Okay. Well, the converse of proposition 4 fails, and let's see what the converse would read. I thought I erased this. Okay, let me erase this again. If ERE is uniserial, right uniserial as a ring, then ER doesn't have to be uniserial. Of course, we're going to do the example features a left ideal instead of right. So somehow that was convenient for me. So take this ring where this is an upper triangular matrix ring where the top left corner has rationals and the others are reals. And let E be this idempotent here. Then the ERE is the corner ring that's isomorphic to the field of real numbers, but RE is this guy, which is not uniserial as a left R module. That's because the top right corner is an infinite dimensional vector space over the Q. So, okay, in the sequel we mention a slightly more generic example in terms of the Endo ring. What you do is you take a projective, hence non-singular simple module, and take its injective E. Because of this non-singularity of S, every endomorphism inside E is the extension of a unique endomorphism of S, and every endo of E is the extension of a unique endo of S. Hence the isomorphy that you see here. But the endo ring of S is a division ring. Therefore, so is the endo ring of E. So that's where the first part of our discussion ends. I thank you for your patience and interest, and see you in the next video.